Now let's look at the solution for this, the conceptual question in electromagnetic waves. This is to identify the modified form of Ampere's circuital law from the Maxwell's equations. Here are the 4 Maxwell's equations. So let us see each equation now in detail, and let us identify the modified form of Ampere's circuital law, which we also called as Ampere-Maxwell's circuital law. So the first equation, as we are finding, it is the surface integral of electric field over a closed surface. The other way, the flux of the electric field through a closed surface area is equal to 1 by epsilon naught times of the charge included in that surface. And it is obviously the Gauss law in electrostatics. So this is Gauss law in electrostatics. Coming to the second equation, the surface integral of the magnetic field over a closed surface is equal to 0. Or this is also, we can say that the magnetic flux through a closed surface is equal to 0. This is the Gauss law in magnetism. What does this equation concludes is the magnetic poles always exist in pairs. As the magnetic poles exist in pairs, the net flux with a closed surface will be equal to 0. Due to one pole, if it is outward, due to the other pole, it will be inward, so that the net flux becomes 0. And an isolated pole is rather a theoretical concept. This is the conclusion we get out of this. This is Gauss law in magnetism. And coming to this, the third equation, the line integral of electric field over a closed path, that is the EMF induced in a circuit. This is the other way, it is the EMF induced in a closed path or closed circuit, is equal to the time rate of change of magnetic flux through that circuit. Of course, here negative sign is in accordance with Lenz's law. This line integral of electric field or the EMF induced in the circuit opposes the very change of the magnetic flux in that loop. This is what Lenz's law says, and that opposition is indicated by this negative sign. And this is simply the Faraday's law in electromagnetic induction, EMI. So this is Faraday's law in electromagnetic induction. And the fourth one, the line integral of the magnetic field over a closed loop. The line integral of the magnetic field over a closed loop is equal to mu naught times times the sum of the conduction current and the displacement current. Here you see, this is IC stands for conduction current, and this term epsilon naught d by dt of phi suffix e, this is all displacement current. So the magnetic field, the line integral of the magnetic field over a closed loop, which is equal to mu naught times the sum of the conduction current and displacement current, and this is simply Ampere-Maxwell circuital law, or the modified form of Ampere circuital law. The Ampere circuital law is, that is, the line integral of b bar dot dl bar over a closed loop or closed path is equal to mu naught into IC. But now we have a displacement current in addition to IC. This is the modification. This is to overcome the inconsistency of the Ampere's law in case of circuits having elements like the capacitor. So that inconsistency is now we overcome by introducing the concept of displacement current. So the line integral of the magnetic field over a closed loop is equal to mu naught times of the sum of conduction current and displacement current threading that closed loop. This is our modified form of Ampere circuital law, or simply we call this as Ampere Maxwell's circuital law, and this is the modified form of Ampere circuital law. So option 4 is our correct answer.